Hello, good morning. Hello, good morning.
Good morning.
I am
Good
ready
morning.
now. Good morning, good morning. Okay. So I am ready now. Shall I start my lecture?
Yes, sir.
Okay. Let me share the slide straight away. Are you able to see the slides?
Yes, sir.
Okay. So good morning, and I must thank the organizers for this webinar and for the invitation and for organizing this webinar on differential equations and the numerics. So what I'm going to talk today is on GPU computing, graphics processing unit computing, and as our industrial case study. These are all connected to flow problems, which involves fluid dynamics equations, which is a system of differential equations. Then I'm going to explain about one of our successful method, one of a measuring method, which is a finite point set method. Then what is the algorithm and what are all the computational components involved. And all these problems, whatever I'm going to discuss, requires real-time simulation. So it's not only the computation, how fast you are computing is also important. So the GPU computing is basically for the computational acceleration in order to speed up your computation. As you all know that GPU is a graphics processing unit. Earlier it was used only for computer games. One of the GPU we normally, that is what we know from the hardware subpart, is produced by NVIDIA. So those who are familiar with the system, so the NVIDIA graphics processing unit is very popular. But now this particular unit, GPU, can be used as a parallel computing. So you don't need to look for a high-end parallel machines. And you are in a position to do your parallel computing. You are in a position to do your parallel computing on your laptop, which is affordable. And also it's GPU based parallel computing is data parallel. You must understand the parallel computing as instruction parallel. Now it's a data parallel. So we have basically have the flexibility of flexibility of having a complete control on our parallel computing, which we can do it on your laptop. So most of the systems, whatever laptop you buy today, it has a GPU processor, and most of the softwares which you are buying already, for example, MATLAB today is based on the GPU processor, GPU computing. And also most of the system software is also based on the GPU software. So your parallel computer is also already in use in your laptop. Sometimes when we use the applications or softwares, we may not be realizing that there is a parallel computing automatically involved. So, but this is very important today because today in the world of high performance computing, the GPU computing and GPU scientific softwares are very important today. And all your scientific softwares like MATLAB, like FemLab, like there are so many Mathematica, whatever you say. So these are all already come up with a GPU. GPU computing, meaning you can do even fast computing with your laptop with those softwares. That's the main thing. But every problem needs its own its own its own treatment. So what I'm going to talk today is our own experience on direct industrial problems and what is the fluid dynamics models. Then I'm going to talk about because it's my focus is on the GPU computing, how you are compartmentalizing your entire computation. Then in each compartment, how much computational speed you are getting. I'm going to demonstrate some of our finally with how much speed up we got. So we have introduced all the GPU speed up measure. We have introduced GPU acceleration ratio, and there are so many things which we have introduced. And right now we are in full flow. Right now the GPU is not only with a single GPU you can do with a high-end single GPU really do quite high speed computation. But right now today the GPU comes in parallel also. So a parallel GPU. So the important point is computing, this parallel computing, in order to get into the speed up, you need to convert the entire algorithm, whatever numerical algorithm, into a proper design, GPU design. Otherwise, we cannot get the speed up. The GPU design is not, it's not that straightforward. One has to really master that GPU design. So my focus is on what we did and what is our contribution here. That is my focus today. And also focusing. So basically, it comes from the problem to mathematical model to numerical method to algorithm to GPU design to computation to speed up. So in the entire thing which will be covered in this another 45 to minutes. I'm audible. Is it okay for you? Hello?
Yes, sir. Yes, sir.
Okay. Okay. So let me go to the talk. So I'm going to, this is my outline of the talk. So first I will introduce what is a problem which we are, I'll show you some of the problem. Then what is the, then I will get into basically the details. Then again come back to those problems in order to talk about the speed up. One of the first the problem which we handle is the manhole problem, which is basically consider the manhole problem, which is the sewage system in urban area, collect wastewater from house to and industries. So what it will happen is the protect streets and houses from flooding. So the company wanted to know if there is a flood, within how much time within how much time or what is the simulation, what is basically the flood simulations, okay? And 1 minute, yeah. Go back please, wait. Yeah. So to protect streets and houses from flooding, overloaded sewage system cause damage due to flood. So they want basically this is the problem. We need real-time simulation, and even we have done it in a three-dimensional geometry. Given a street geometry, then given where that particular flood occurs, then how the water comes from the sewage system gets into onto the streets. So this has to be simulated because in order to have any automated control, we need to have a real-time simulation. So this is the two-dimensional. This is the three-dimensional manhole flow, and it's a 2D manhole flow. We will show you how we have done it later. You will understand this simulation in a later part. So you look at the right hand side. So the simulation in the latter part. Okay. The next problem is a rolling fluid in a box. Basically, the companies who are produced thin films, for example, a window screen and a car window screen. Then even in buildings, you have a room with glass windows. So the films, thin films on this type of so this production of this particular thin film in here in India is the Saint Gobain. They are producing this one of the big producers. And in Europe, it's a Scott company who are producing. So we have a project with them. It's a fluid in a box rolled into a thin film by 2 rolls, assuming no gravity. And the rolls are filled with different high viscosity fluids and cooled at the inside. The moment it comes to the rolling part, then it becomes a thin film. So what the company, basically they are using 3 different materials, glass, left roll and right roll. Rolls basically outer circle in contact with the 2 different materials. So we have done a project, Scott Glass project. In India, it's the branch is Saint Gobain's company who are producing the large glass. We'll understand the meaning of this. So this is the entire production line, raw batch and furnace. Then what is given to us is this particular part, coating. This is the one float part. This is the another way of having a thin film. But what we are focusing is on this particular simulation. So you just see, I will show you. You look at the right hand side. So molten glass flows down to ramp onto a batch of tin, bath of tin, a simplified model of glass floating process. Then only included buoyancy forces acting upon the lower surface. Glass can tip the tin level. We have a free boundary for velocity and a Dirichlet boundary condition for pressure. So glass flow from upper left to a lower left side. I will show you the simulation. You will understand. So this is the one, that particular piece which I have shown. That is the one where in the industrial process. So the glass is the molten glass is basically flowing here. Then it is coming and settling here as a thin film. Now you look at there is a streak. You look at the figure carefully. This video carefully. There is a streak. This is the simulation of our numerical experiment. So now you see that this is the streak. So the company do not want to have the streak to form. In normal case, what they do is the company, because otherwise what will happen is you imagine your car window where the thin film having some kind of bulge, or your TV screen having some kind of bulge. So in order to avoid this, the company in normal situation, they have to stop the process, then they have to redo the entire process again. So what they wanted is it possible to identify through the simulation at what time the streaks will occur once the process starts, at what time the streaks will occur, so that they try to have the control at the beginning in order to avoid the streaks basically, and also there is no stop in the production line. So you keep on producing, but you have a control, automized control. So they wanted to understand through your mathematical model what time the streaks are expected. So you just see this. This is the one. You can see it nicely that there is a bulge, that's called streaks. So glass production, Scott glass are originating at walls of the glass ramp. Streaks occur in glass melting, and the streaks have different physical properties. Difficult to avoid formation of the streak. That is a natural. But if once you know that at what point of time the streaks will form, we can have a control in order to make sure that the streaks are avoided. So that is the thing, so that you don't need to stop the entire process. This is a very important problem from this company. And another is the sloshing problem, which is you just see this simulation. It's a result of our simulation. So the sloshing problem is very important for designing the petrol tank in cars. Then so what is it's a free surface flow problem. All your problem, for example, flood flow is a free surface flow. This is also the glass flowing problem is also thin film. It's also a moving boundary problem, whereas sloshing problem is a free surface problem, which is important for designing the petrol tanks. Okay, I'll come back to these examples again because these are all some which all these problems requires real-time modeling, real-time simulation. Then we need to have it's not necessary, it's not enough you have only the mathematical model and appropriate boundary conditions. As you know that the models, most of the models cannot be solved in an exact form. There is no exact solution, closed form solutions. Then we need to look for a numerical methods. We need to devise our own numerical method. Even that is not enough. It has to be computed in a real time. Otherwise, the real time simulations cannot be implemented. That is the main. So I'll go to the next part. So motivation, we need an efficient numerical method, fluid dynamical problems with free surfaces. In films, you have a multi-phase flows. And there is a fluid structure interaction, which we have seen it here. Strong chance of computing domain. For example, flood flow is basically the fluid structure interaction. And you have a structural mechanical problems with a substantial structure changes. So the method which you are using is a finite point set method, which is a very successful method. And I am basically collaborating with this team. And the real-time simulation of FPM, the finite point set method is a challenge. So here we started with the GPU computing on FPM. That is our focus. There are a lot of literature survey on GPU. Starting from 2010, last 5 years last 10 years it is becoming more and more popular and more important. So there are a lot of literatures and so now you look at this flow chart. This is very important. I'll come back to this flow chart. This is a CPU and this is a GPU. What we have used is one GPU with the laptop. What I am using it here. Laptop. So you have a CPU. You just see that there are different components: initialize data, transfer data to GPU, particle management kernel, callback data from GPU, matrix computation, matrix operations kernel, then get AUPR from. You will understand what I mean by all these things. Then launch by CG-stab. By conjugate gradient stability method, get results from GPU and save. So what is happening is the CPU components, the CPU part is here, and from CPU, which are all the components getting into the GPU, which is important because you need to spend a lot of time in CPU. So those operations need to be get into the GPU. The moment you go to GPU, we do particle management, which computes because I told you. We are using a numerical method, which is a mesh-free method. We need to do a lot of particle management. Under the particle management, we have most time-consuming is neighborhood searching, sorting. Then we need to insert particle. We need to remove particle. So this is a particle management kernel, which is go to a GPU. Normally in GPU, from CPU to GPU, we call it through kernels. So one of the important time-consuming kernel is particle management. Under particle management, we have neighbor search, we have sorting, we have insert the particle, we have to remove the particle. Another important component is matrix operations. We need to do matrix multiplication, matrix vector multiplication. Then we need to do matrix inversion. So that is another important component which takes considerable time. It has to go to GPU in order to get the speed up. Then we need to solve the biconjugate gradient stability kernel, which basically to solve the large scale systems. It's a biconjugate gradient stability method written in GPU, and over which we have to do scalar product reduction. We need to have a matrix. There's all these things as sparse matrices should be stored in a efficient compact storage. We cannot use arrays because it's a huge size, compact storage. So along with that, you need to solve you need to solve the system of a large scale system of linear equations which occur due to your numerical method. So what are all the operations, and from where? From CPU, what are all the important things going to GPU? Particle management kernel is one, matrix operation kernel is one, BiCG stab kernel is another one. You will understand this again in a much clearer way once I come back. I'll show the slide again later. So in this entire computation, because I said it's a GPU acceleration, so you need to worry about how efficiently we are accelerating the computation. Basically, how efficiently we do the speed up. So once you look at all the simulations, whatever I have shown, if you look at the computational level, I have to compartmentalize the entire computation. See, for example, 20 plus 15 is 35, 45, 55, 65, 75, 85, 100. So if the total computation is 100%, now 20% goes to FBM matrix linear solver. I told you there is a linear solver which we need to do. So the linear solver through finite point set method, grid tree method, this takes 20% of my computational time. FBM matrix inversion, you will understand I need a matrix inversion. Every step, at every point, and every time step, at every point, I have to do the matrix inversion. That takes 15% of my computational time. I'm doing a lot of neighborhood search. That takes 10% of my computational time. I'm using merge sort in order to do the particle management. And that is also again 10% of the time. Add and remove particles, as I told you in GPU, that takes another 10% of my computational time. I am doing a lot of scalar products, that takes another 10% of the computational time. Particle initialization, which I need to do it, then that takes 10%. Then other miscellaneous calculation takes 15%. Unless you have a clear blueprint of this, what type of components involved in your entire computation, especially in GPU, we cannot have the overall speed up is computed based on in each component how much speed up you are getting. So I need to have a speed up in this. All these blocks, whatever I have written in this particular pie chart, whatever I have given, in every pieces, I need to have a speed up. Then only I can get the overall speed up. So that's more important. So you should have any real-time computation, that too a problem involving a direct industrial problem, involving that is, then we need to be very careful in how you are compartmentalizing your computation. Then in each compartment, how much speed up you are getting. It's not necessary that every component you are able to do the parallel computing, especially the GPU parallel computing, because it's a data parallel. So don't think that every problem can be converted into a data parallel and do it under GPU. You have to have a very clever plan in order to make sure that you have a design, GPU design, and because your entire data structure changes. Your algorithm changes, and we need to see whether the parallel computing is possible at this particular component. So, what is the governing equation? All these problems, manhole problem and thin film problem and sloshing problem, there are some more problems which I am going to show it up later. But in all these problems, what is the base governing equation? Basically the template equation is a Navier-Stokes equation, incompressible Navier-Stokes equation in a Lagrangian form, because I am using a mesh tree method. The mesh tree method is It's a particle method, and it's in the solved in the Lagrangian form. So the Lagrangian description, basically you are traveling along with the particle. Okay, you are not sitting in one point and observing. That is Eulerian, but you are sitting on the particle and traveling along with the particle. So it's a Lagrangian form because this methods you are traveling along with the particle. Okay, because all your computation, moving boundary and free surface, and all this computation needs we need to track the moving boundary. We need to track the free surface. We need to track the movements. So in order to track the movements, the Lagrangian, especially the boundaries, you need to have a Lagrangian formation so that you are along with the flow, you are traveling and understanding what is your moving boundary, what is your free surface, and so on. So d by dt, capital D by dt, is a material time derivative. All of you know. So the dv by dt is minus 1 by rho gradient of v plus nu del square. This is a Laplacian operator. V plus the forces G, and divergence of V is 0. Okay. So if you look at the capital D by dt is a material time derivative, which is nothing but del by del t plus V dot del on V, which is basically the Navier-Stokes equation. The first equation, since it is an incompressible flow, it's a divergence free. There is a mistake. It's a divergence of V equal to 0, not that Laplacian. The divergence of V is 0. It's a del operator, and this is the Laplacian. This one is the Laplacian. Rho is the density, V is the velocity, G is the body force acceleration, mu is the viscosity. It's basically the kinematic viscosity, and P is the pressure. Now, all the problems we can use mixed type of conditions. On solid wall, we use a free slip, no slip condition for V, for the velocity, which is V is 0, and del V by del N, N is a normal direction. So unit outward normal. So dot T equal to 0. T is a tangential direction. So T dot N equal to 0. Inflow boundary conditions, V equal to V in, and the pressure del P by del N, the directional derivative along with the normal direction, rho G into or dot N. Outflow boundary condition, for pressure is P equal to P out, whereas del V by del N equal to 0. On the free surfaces, because sloshing problem needs a free surface, which is tau dot n minus Pn equal to sigma kappa n, where sigma is surface tension, kappa is your curvature, and tau is your viscous tensor. So your boundary, according to each problem, we may have to put the combination of these boundary conditions. Not that every problem needs all these boundary conditions, but we may have to use the combination of the boundary conditions. Okay. So now, if you go to the numerical method, the skeleton of the numerical method, because I need to have the entire flow simulation. So if you understand, I have a divergence of E equal to 0, then d by dt, the Navier-Stokes equation. Then basically I need to approximate the spatial derivatives. I have, for example, I need to approximate the spatial derivatives. If I go back to this equation, so I need to approximate, I need to find out P. Then I need the P at the same time in order to compute the V at the same time. Then this involves Laplacian operator. So second derivative, space derivative must be approximated. Then your gradient of P. Once you have P, the gradient of P has to be approximated. Then here you have a dot product. So all these things and the divergence of V, all these things has to be taken. Do you have any questions, sir? Is it fine? Hello? Any questions? Please stop me if I am slightly fast or.
Sir, we will be having question answer session in the last 10 minutes.
Fine, sir. Thank you, sir. Okay. Now, since it is a Lagrangian formation, so what I do is, first equation is dx by dt equal to v. So that is xn plus 1 equal to xn plus delta t into vn. Since I need the pressure I need the gradient p at the same time in order to update my velocity. I am introducing a artificial velocity v star, where I am solving. So you understand. In order to avoid this, what I do is I am introducing v star in order to take care of not the gradient p part. In order to take care of this, then from v star to v. See, I am from vn nth time to v star, intermediate time I am going v star, then v star to vn plus 1. The V star is my numerically or artificially introduced velocity, which will not satisfy the divergence of V. V at time n will satisfy. Vn plus 1 at V at n plus 1th time will satisfy divergence of V equal to 0. But V star will not satisfy because it is my numerical part. So what I do is I am projecting. Is basically it's a projection. So what I am doing is I am coming from Vn projecting onto V star. From V star I am projecting onto Vn plus 1. So what I do is, in order to, because I need P, gradient P at n plus 1th time in order to find the velocity update at n plus 1th time. So what I am doing is I am for the entire simulation, what I am doing is I am doing the Chorin's projection. So Chorin is one of the famous fluid dynamics. I think many of you know about his book on mathematical introduction or foundations of fluid dynamics by Chorin. Is a Chorin is a very, so his method, Chorin's projection for the numerical simulation. So dV by dt with V star, I am doing only these two parts. Then once I know V star, then I am using V star to Vn plus 1, I am using this gradient. By then I know my P. So that's what my idea. Okay. So you need to know the pressure at the same point in order to pressure at the n plus 1th time in order to compute the V at n plus 1th time. So V star is Vn plus, I am not using the pressure term here. I am using Laplacian V at n and delta t into Gn. What is in step 2? Now I am updating Vn plus 1 using my V star, where I know at that time Pn plus 1 and gradient of P at n plus 1th time into delta t with the incompressibility constraint that divergence of Vn plus 1 equal to 0. So how do I get P? The pressure is basically, what I do is I take a divergence here. Divergence of Vn plus 1 is 0. Divergence of V star is not 0. The moment I have divergence of gradient P, I have a pressure Poisson equation. So I will be solving the Poisson equation for the pressure, which is a boundary value problem for P. So pressure Poisson equation at n plus 1th time. Then I have a divergence of V star divided by delta T. So how I am doing it? I take a divergence on Vn plus 1, which is 0. Divergence of V star is not 0, but the divergence of gradient P will become Laplacian. So now I rearrange it. Then I'm getting this particular divergence. So by the now I'm solving this. Since I know V star from Vn, I can compute divergence of V star. Then I can solve this pressure Poisson problem for n plus 1th time. Once I know my P, I can compute my gradient P at n plus 1th time. Once I know the gradient P at n plus 1th time, then I know my V star and gradient P n plus 1, then I can update by Vn plus 1. Then I can repeat the process for the next time. So this is the way the entire simulation gets in. But before that, you have so many computations to be done. So you need to find P through pressure Poisson equation along with the pressure boundary condition. Then we need to compute gradient P. Then we need to compute the Laplacian V at n. Then you need to compute the divergence of V star. Please understand. We need to compute the divergence of V star in order to complete your pressure Poisson equation. So all your spatial computation has to be done. We use del P by del n plus 1, del P at n plus 1 equal to 0 at the time n plus 1. Digital boundary condition for free surfaces. Outflow particles where we use P equal to P naught plus sigma k for the free surface and outflow particles. Outflow particle means when it is going out of the. So spatial derivative approximations are done by finite point set method. So what is finite point set method? I'll quickly get into this one. It is a mesh-free method. It is not like a finite difference or a finite element or finite volume method. So finite difference or finite element or finite volume requires a lot of meshing. The meshing takes a lot of time, especially in this type of problem, moving boundary and free surface flow problems, and that too industrial problems needs at every time we need to we need to generate the mesh. Then we need to have a control on the mesh, which takes a lot of time. So it's better to have a grid-free methods. Then you allow it to like a mesh-free with the Lagrangian idea, Lagrangian formulation, so that you are able to track the boundaries. So you don't need to do the meshing at every. So it's a mesh-free particle method, Lagrangian method, where the numerical particles carry the fluid information such as velocity, density, pressure, etc. All your physical quantities. Now let us get into how I am solving a Laplace equation. So Laplacian u equal to f with a general boundary condition with a u dot del u by del n equal to g. Basically, del u by del n, you have a normal components nx, ny, nz, ux, ui, all the velocity components. So now, here it is p. What we are going to use is p. So del p equal to f. Sorry, del p. What I am saying, Laplacian p equal to f. Then del p by del n equal to g. So this g is not a gravitational force; it's a function g. Okay. So consider the domain omega. Let us particle xi is you are basically throwing the particles into the entire domain. So this is the exact picture how the particles are shown. And every particle I am labeling. Then I have a neighborhood, and this is important. That's what I told you. You have a neighborhood search. So you have a global particles. The red particles are global particles, and the white ones are the neighborhood particles for that particular center point. You will understand quickly what I mean by that. So you use this. This is the neighborhood. The red ones are basically, so this is the x particle and h is the neighborhood length. So all your spatial approximation is done by the neighborhood. So and the red one, whatever particles I listed, it's a global particles. For every global red ones, every particle of that global red one, I need to have a neighborhood list. So this is in the spherical. So you have with the smoothing length h. What is your neighborhood size? With the smoothing length h, you have to basically compute because all your spatial derivatives are approximated by a neighborhood particles. Okay. So it's very important that you are traveling and every particle you have to do the neighborhoods, approximate the spatial derivatives. In order to do the approximation, the spatial derivatives, I am approximating with the neighborhood particles of a smoothing size h. Okay. So how I am demonstrating, for every particle, I need to evaluate. Suppose if I have a function u, I need to evaluate the first derivative, second derivative, and so on. So that's what. Expand u. Don't take this as a velocity. My velocity is v there. I'm just for demonstration purpose. How I am solving the finite. What is it? The Poisson problem. Laplacian u equal to f with the del u by del n equal to g. If I have such a Neumann boundary condition with this problem, how I am solving through the finite point set method. The first part in the finite point set method is given your domain, basically you put the particles, then at every particle, all these particles are global particles. Then for every particle, you need a local particles through the neighborhood. So this has to be demonstrated. So every global particle will have a neighborhood particles. It has to be generated. And now you are moving with the time. So you move with the time. The next time your neighborhood will change. Again, next time your neighbor will change. So every time you need to search for your neighbors because the neighbor particles are important in order to approximate your spatial derivatives. So you understand how now I'm solving. Not only that, I'm solving the boundary value problem, which is del squared u equal to f with the del u by del n equal to g. So UJs are expanded. UJ means this j equal to 1 to m is my neighbors. So that's what I told you. Please, for every global particle, I varies from 1 to n, which are all red ones. We have a neighboring particles xj, j varies from 1 to m, which is in the right, which is in the white color. Okay. So in this picture, red ones are global particles, and this is your white. So now you see that this is my neighbor. Okay. So I need to have a neighborhood list. So that's what j varies from 1 to m. I need the Taylor's expansion, and I am trying to expand it along for all the neighboring particles. J varies from 1 to m. Now my thing is all the first possible derivatives, all possible second derivatives. H is your SCN matrix. This is the gradient U. So then what is happening is you will have I need Ux. For example, in this problem, if I'm solving it for 3 dimension, I need Ux, Uy, Uz. Then I need Uxx, Uyy, Uzz, and Uxy and Uyz. Okay, I need to have derivatives of this. So in order to do that, what I do is I expand J for every neighborhood particle about that point X, I am expanding. So for every neighborhood particle, so you see that for every J surrounding there, I am expanding about X. Okay. I do the process for every particle. So J varies from these are neighborhood particles of the point X. Okay. Now I am expanding Uj. Now if you look at how many I need U, I need Ux, I need Uy, I need Uz, I need Uxx, Uyy, Uzz, Uxy, Uyz. So I need in total about 3 plus 3 plus 6 plus 2. Basically, I need 8 derivatives. I need 8 derivations to be approximated. So that's what I do it. So when I do it, you have a more number of particles, U1, U2, but you have less number of unknowns. Unknowns are Ux, Uy, Uz, Uxx, Uyy, Uzz, Uxy, Uyz, and Uxz and Uyz. Okay. So this has to be solved. You cannot. It has to be solved only through the least square approach. So basically, what I do is I'm attaching the equations Uxx plus Uyy Uzz as a extra. So if what I'm doing is this is from the expansion. J neighbor particles with respect to x. Along with that, I am doing with equation Uxx plus Uyy Uzz equal to f, and along with the boundary condition Uxnx Uyy Uzn equal to g. So now you look at, you will have more number of points and a less number of unknowns. Your unknowns are all the derivatives, possible derivatives. So basically the meaning you have more equations plus less unknowns. Okay. So then it has to be, so you have, I'm using error, this term is error for every point. Then when I'm writing it in vector form, which is equal to MA minus B, where M is exactly this one. Where dx1 is nothing but, dxj is nothing but xj minus x. Dyj is nothing but, dx1 is basically, here I'm changing into, so dx1, dy1, dz1 for the first particle, second particle, mth particle. Then dy1 is yj minus y1 minus y. dz1 is z1 minus z1 minus. So dxi is xi minus x. dyi is yi minus y. dzi is zi minus z. So then I have the all possible second x1 minus x2 whole square. When in your Taylor's expansion, you see that the second term will have a square. So then I have the cross products. Then when I'm writing this this particular pod uj, j varies from 1 to n in the matrix form, I will get it this way. I'm taking this e to the left side. This becomes na minus b, where a is my unknown, where a is u, all possible first derivatives, all possible second derivatives, and your b is nothing but the neighborhood information u1 to m f and g, where h u denotes the components of h, meaning SEN components. So this will give me the A. So actually I want what is approximation for me, the A for every point. So this will give me my A, which is n transpose Wm inverse n transpose Wb, because I am using the moving least square, weighted least square idea, because I am minimizing the error. I am basically minimizing the error. So in order to minimize the error, I am getting this particular, the weights are basically in your W function. So M transpose Wm inverse M transpose Wb, which will give me fundamentally using the least square method, because I wanted to minimize error. I'm minimizing the error. So what I'm doing is I'm constructing a cost functional j, which is a function of e, which is nothing but summation. You have wi ei squared, I varies from or j varies from 1 to m. Plus, I have a boundary particles equation corresponding to equation. I have a en plus 1, en plus 2. Okay, because I am adding the equation and constraint as along with this one. So this along with the equation, along the boundary conditions is one full set. Okay, which I am doing. So this needs A is approximated finally through the finite point set method, meaning the all possible derivatives including u are computed fundamentally from this particular, at every point you need to expand. That's why I told you need a matrix inversion. So you need to compute the matrix product, matrix product, you need a matrix inversion, which will be by, if it is a 3-dimensional problem, it will be 10 by 10. It is a 2-dimensional problem, this will be 6 by 6. If it is a 1-dimensional problem, this will be 2 by 2. Okay. So now you see that it has to be computed. You need to spend time on these products. You need to spend time on the inverse. You need to spend time on this. Then, in order to do this solving the u, what I do is I am solving it because I have to solve this. Once I know u, I can compute all the derivative. But the problem is here I need to solve u. So this has to be computed. I am forming this set of linear equations. This linear equations, because please understand the u which I am getting it here, a, if I am pushing it here, the a will have, the a ultimately will have the first component as u. That u will have the corresponding information which I am having it here. Okay. So I am forming a system of equations for my u at every point. It's a globally. This is at one point at globally, because for one point I have explained, but now for entire capital N points, you will have a system of equation u1 to u capital N, which will form this. It has to be solved through, what we have solved it through by conjugate gradient stability method. So this is a SWOT system. This takes another 20% of your computational time goes here. Okay. So it's clear that we compute not only the value u but also the derivatives. U derivatives whenever you look at PD or OD. Complex geometry, free surface flows are possible. These are merits, wide range of application in industries. What is the demerits? It requires millions of particles to get efficient solution. Require always at every point. Requires constant particle management, and to solve the SWOT system, you need A input at each time. And computationally costly, and that is why we have to address all these problems. Okay. So now the GPU acceleration, we have focused only on where you need the GPU acceleration. You need the GPU acceleration on the linear solver, neighbor search for each particle, merge sorting for each neighbor list, particle management, and matrix inversion for each particle. Okay, so these are all the things which requires your the GPU, because this is the one which I need 20%, 15% here, 10% here, particle management, another 15%, Matrix inversion, again another 15%. Okay. So Z indexing, each particle is copied into a block's shared memory exactly once. So where I'm using Z indexing, you will understand. Each copied shared memory is used all other threads. So now I'm talking about how we have put the entire thing in my GPU. So basically, we have used Z indexing. Okay, every block, because if you look at GPU computation, you must understand when you write a program, you have a grid. Every grid, you can have as many grid depending upon the size of the GPU. Every grid will have blocks. Every blocks will have threads. Every thread will carry your data. So, and all these things are connected to a shared memory. The shared memory is a memory for all the GPU grids and which can be shared. Also the memory which can be shared to the CPU. Okay. So this is very important because the shared memory is for, because the GPU has the grids to blocks, blocks to threads. Then every grid, inter-grid communication, you can do it through shared memory. Inter-block communication, you can do it through shared memory. And GPU to CPU computation, you can do it through shared memory. Okay. But it's always a good idea to put in maximum thing into GPU, finish the entire process, don't have a communication always from GPU to CPU and vice versa. So now what I do is in a particle management, I wanted to show you what we do is each particle is copied into a block shared memory exactly once. Each copied shared memory used for by other threads. That's what I told you. Okay. So whatever particles, we block it like that and put it in your one particular thing, put it in your CUDA threads. It's called GPU and the programming is CUDA. What I'm saying is the CUDA is your programming part, GPU is your hardware part, CUDA is your programming part. That's why today you need to use a CUDA C++. It's not only C++, it's a CUDA C++. Okay, meaning you are writing a program for the GPU. Okay. So now we put these blocks and put it in your CUDA threads, which is a CUDA block. Block will have a CUDA threads, and the red points will go to this one, which in turn will be shared by will be having information in the shared memory. Now you see that every domain is the block is right now going into this one. Now you see that it's only a demonstration purpose, a CUDA block and how the information. So now we go to the neighbor search. Okay. Result indexing is I'm using it for neighbor search. So the neighbor search is basically we put it into blocks, and then I say that through this particular blocks, I am saying that I'm searching for the neighbor. So the algorithm which I am using it for neighbor search is the voxel method. Basically the vortex voxel vortex method, which is called construction of voxel structure. So the GPU algorithm will look like this. So particle from CPU goes to GPU, and ith particle, each thread access each particle, ith particle. Then what I do is I call the voxel of I, which will give me, and in order to keep the particle in a particular form, I am using a merge sort because every particle is labeled. So along once I know the searching, after the searching, I know the neighbors. For every global particle, I have a neighborhood list, but this neighborhood information will be in the sorting form because it is easy for you to access. Okay. Copy sorted particle in an array, build CUDA textures to the sorted particle. So this is the way where we do that. For each block, we find a voxel inside the ball and the indices of the particle from first release. So basically what I do is for I less than n, keep on doing voxel I, then you do the merge sort. then sorted particle in an array, then for each block you do the same thing and save the neighborhood information and box instruction for that. This is only a skeleton I am giving because in a short time I cannot explain the complete. So now you see the neighbor search. Basically, we do it in this way. This is the figurative how we are doing in the neighbor search. Now there is a Z indexing. Each particle is copied into a block shared memory. So that's what, and each copied shared memory. That's what I told you. Now you see this neighbor search. So voxel method. Then I am using particle management. Particle moves with fluid velocity. Particles may cluster or scatter. If particles cluster, produces high computational effort. Numerical instability may come because as numerically we need to have a control on particles. Particles scatter. If it's scattered, then spoil accuracy and cause problem in neighborhood search. Constant particle management is necessary. Two close particles have to be removed. Holes have to be, if the particles are not enough, then holes have to be removed by new particles. So information is available where the points are, information is not available where there is no points. Okay. So we do it with the Voronoi cell. Voronoi cell is a point of a point. Xj is a set of all points closer to Xj than to any other point. And what we do here is we insert new particles in identified holes. Field data for new particles is interpolated from its neighboring particles. Arithmetic mean in case of one-dimensional problem. Shepherd interpolation and moving least square approximation for higher dimensional problem. You see that this demonstration will show you that where we need to add particles. So here is a place where we need to add particles. Here is a place we need to add particles. Okay. Here is a place too many particles. Here is a place where we need to have a mechanism of adding particles and removing particles. Adding particle, then the information of your physical quantity information like pressure, density, all the information has to be shared in that particular thing because ultimately it's going to be a conservation equation. So it has to be properly. If you remove the particles, you are removing the information. So it has to be distributed with the available particles. So that is more important. It's not only you are just removing the particle. You are not only you are also removing the information about pressure, information about velocity, all the physical quantity which you are using it. That information about those points are also that has to be distributed. So we use this now. So it's easier than adding particles. Removing particles is easier because finding closest points, close particles are merged with, remove them and insert these new particles. And you update your U, which is a physical quantity, with this information. So this is the particle management in GPU, how we are doing. The entire thing is done in this particular fashion. So it's only a demonstration purpose. I will show you how we are. Sorry. So now this is the particle management, the algorithm written in GPU. So of course I cannot explain. Manage boundary particles, which is in GPU. Then we use in order to understand how many points you need, whether to remove or we need Delaunay triangulation. Then interior particle management, which you do it at this GPU. Then so this is basically the skeleton algorithm skeleton. The next component, as I told you, so I have talked about the particle management. I have talked about adding and removing particles. I have talked about neighborhood search, neighbor search. I talked about how to store the particles in order to do the computation. Now I am coming to the storage because I need a linear system and when I am solving a Poisson problem. And the sparse matrix has to be stored in a compact form, which I use the CSR, compressed sparse row format. General purpose sparse matrix representation. Stores column indices and array index. Stores data and array data. Row pointers takes the CSR representation. So this has to be converted into, that's what this, as I told you in my previous FPM, I need to solve the linear system AF or AU equal to R. This has to be computed here. So I am using the compact storage representation. So this is the way which I am using. So I need algorithm, corresponding GPU algorithm for this, because all this CSR compact storage I am doing it in my CSR kernel. I am doing it in my GPU. Now, matrix inversion. That's what I told you. There's another important operation which I have to do, which is a matrix inversion. At every point, I need to approximate the first derivatives and second derivatives. I need to do this matrix inversion and matrix multiplication. Inversion has to be done for each particle. Each particle has to get inverse of a 3 by 3 matrix for 1D problem, 6 by 6 matrix for 2D problem, 10 by 10 matrix for 3D problem. And we have used least square to invert it. So this has to be inverted, and as far as possible, try to do this in a exact form. So that is also we have done it. So this is the GPU matrix inversion algorithm. So that's what when you're defining GPU, you see that I is going to the thread, and the thread is in this block, and later you can see that since I'm using only one grid, and the array you can see that which grid it can go. So that so this is the basically I'm using how the matrix inversion is done at the GPU. So I have done a GPU for particle management, which will have add and remove particles. I have done the GPU for neighbor search. I have done the GPU for compact storage. I have done the GPU for matrix inversion. Now you see that how the two-dimensional, I'm sorry, I just, so this is the matrix inversion. Then I have a BiCG step also I have, which will come, particle management. So particle management, this is a storage. This is the CSR kernel, then matrix inversion, which I have to do. Then I am doing the GPU algorithm here. Then I am just showing the two-dimensional broken dam problem. It's a dam is broken, and I am just showing how much particle we have taken, 136,100 particles, and what is the speed up, GPU speed up I have demonstrated. And here is a way where you can see how it is. So this is on the three-dimensional, say three-dimensional broken dam. You see that how these are all our simulation, free surface simulations. The previous one is for the two-dimensional problem, broken dam. Now you see that it's a three-dimensional broken dam. How much? I have taken almost 1 million particles. Here. It has to be computed in the real time. Okay. All these things are our computation of the GPU on the FPM on the incompressible area strokes along the appropriate boundary conditions using the Chorin's projection. So this is the shallow water things. You see that I have taken that's 1 million particle, but I have taken 3 million particle. You see that the shallow water, how it is. You see that the kind of visualization we have. So this is the result of this. What I am in this x-axis is the number of particles. Y-axis is the GPU speed up. So basically, as a particle size in particle increases, not the number of particle increases, your GPU speed up is also increasing, but it goes to a peak level, then we can. So we need 3 million particles, 30 lakhs, please understand. 30 lakhs is a huge number for your computation, which we have demonstrated, done it through on a laptop, what I am using now, and on a real time. So the GPU matrix is basically, in order to compute the speed up, we need to have a general matrix, which I call it as occupancy, number of VOPs co-scheduled per shared memory, maximum number of VOPs per SM. Okay. Now we have computed two GPUs, GPU1 and GPU2. GPU1 is from Germany, GPU2 is my laptop. So we need to understand, because GPU computation is architecture-based computing. Unless you know the architecture, unless you know the GPU, what is happening there, we cannot. So it's very important that what is the architecture. We should know what is the configuration of the GPU. So because it's very important that in order to compute your speed up, in order to compare your speed up, you should understand, as a scientific computing person, it's important that you should know the GPU architecture. Otherwise, it will be impossible to compare, and also in order to have a metric on speed up, this is important. So I have shown you two GPU1 and GPU2, and how we have introduced the GPU.
Hello. Sir, we request you, please
Yeah.
conclude within 15 minutes. So we
Okay,
request
fine.
you. Okay, thank
Yeah,
you.
fine. I will conclude in 5 minutes, sir.
Sir, yes, sir, take your time. At least I request you to take 15 minutes, sir.
Okay, fine.
Thank you.
So,
Thank you very much.
what is happening is, it's very important that you should have its architecture based, which GPU and what is the configuration. Especially you should know how many number of blocks per SM, which I call it as eta max. Maximum number of threads per VOP, which I call it as pi. Maximum number of VOPs per SM, I call it as gamma max. Maximum registers per thread, I call it as eta t max. Number of registers, I call it as eta. Registers, register unit eta u. Shared memory unit is alpha u. Maximum shared memory size is alpha. VOP allocation unit is gamma e. This is important in order to understand the GPU metric. This is a metric which we have introduced. So how do you know the speed up? Because how do you know that in general for this type of class of problem? Please see, if you look at the first problem, it is a flood flow problem. Second problem is basically a thin film problem. Okay. Third problem is a sloshing problem. Then I have shown you two demonstrations, our results on two-dimensional broken dam problem and three-dimensional broken dam problem. So if you look at all these problems, you have basically, how do you know that you get speed up in all these class of problems? Because I am using the same equation. I'm using the same Navier-Stokes, incompressible Navier-Stokes equation. Only thing, I change my appropriate boundary condition. Then I am using the Chorin's projection for the entire numerical simulation. Chorin's projection. Then in order to approximate my spatial derivative, I am using finite point set method. Then how do you know that the speed up cannot be obtained by problem? How do I know that this works for all the, if I am changing the data even for a particular problem, how do I know that I will get this much speed up? So you need a general setup to understand a metric, GPU metric to understand. That's why all this information is important. I have introduced gamma max, eta max, pi, eta t max, alpha u, gamma au. These are all very important in order to understand. So that is why I put gamma sm. So all these things which we have, that's what, whenever I talk about eta pb, then eta pb is basically register unit, okay? So pb, then you need, it is computed basically based on that, on the GPU1, on the GPU2. So it varies from which system you are using. Which system you are using, which system you are going to install, and so it's all important because you need to have the speed up. I cannot say that you get a speed up whichever machine you are using. It's very important that which machine I am going to install it, which machine I am going to use it. If I am going to another machine, it has its different GPU, then there also I have to adjust the thing in such a way that I should know what exactly I am getting. That's what I tell you. Eta PB is this formula and GPU 1. Eta PB is this one and GPU 2. These two are two different configurations. Architecture. So your computation has gone to today the computation is architecture based. Earlier when you write some program, you never bother which system, what is happening inside the system. But now we need to understand what is happening inside the system. How we need to have some idea blueprint. We are not expert in hardware, but what is the kind of memory, what is the kind of hardware we are using, what is the kind of GPU we are using in order to define our metric. In turn, we get a speed up. Okay. So then we have introduced at limited to alpha. So then we have psi, which is minimum of this. So now occupancy is basically defined occupancy of lambda, which is gamma PB into psi divided by gamma max. So we have a proposition. Lambda is a function of mu required B, mu required T, and alpha PB for a fixed GPU. So then another thing, your lambda lies between 0 and 1. Obviously, lambda cannot be basically. This is also we have proved. Now there is another thing which is called volume. So volume of data transferred between SMs and device memory is the sum of the number of transactions of each multiplied by the transaction size. That is V equal to Ni star Ti. So the earlier ones, if you look at, I am defined the GPU metric for the occupancy. I focused on occupancy. Then I went into what system I am using. GPU 1 on one system, GPU 2 is on in my laptop. Then I talked about all these things. Then finally I talk about what is occupancy corresponding to the systems. Okay. Then the next GPU important thing is the volume. What do you mean by volume? Volume of data transferred between SMs and device memory is the sum of the number of transactions of each multiplied by the transaction. Now, average bandwidth. This is also important. Utilization. Average bandwidth utilization. Suppose A1 ATA or M data required in compute A, then the average bandwidth utilization defined as this. Well, delta I denotes the ratio between number of bytes used in A and transaction size A. So now, when you go to the I'll again go back to the neighbor search. So voxel structure. For each voxel, the indices points is contained in it. For each point, which voxel is contained in it. For each point, which are the points closed by R. Now I generate a list, generate three kinds of list, loop over all points to compute voxel, sort first with respect to voxel indices, test voxel and its neighbor. Then I talk about average bandwidth utilization because this is important. Then I talk about the indexing algorithm. What I am having the Z indexing algorithm. Okay. Then I talk about neighbor search. Then how do I do the voxel structure? Then what is the merge sort? I am using here in GPU. So this is basically the global means it goes to the CPU, share the them. Then how I am using it in. So now, if you look at the neighbor search and GPU acceleration, so I told you 15 plus 4, 14. So neighbor search and merge sorting put together, I'm getting 29% speed up for algorithm of 2D. Okay. Particle management, I have explained already. I don't want to tell, which I am using for myself. I am repeating the same thing. Why I am repeating the same thing is, here I am giving you how much computational time it involves. So this is the particle management algorithm, which I have shown you already. Then I have, so particle management, I am using basically particle management, I get 8% speed up. I cannot get more than that, 8% speed up average on an average. Okay. In here I am getting 14%, 29% speed up together. Here I am getting 88% speed up. In CSAR storage and solving the linear system, and I'm using Sparks vector multiplication. I need all the saves computational cost, useful for iterative methods. I'm using SPMV applied in large scale linear systems. Then this is the CSR kernel, which I have already explained. Scalar product reduction, which I told you, you need a scalar product reduction, which has to be written in GPU. Then I am using the scalar product, so already 29 plus 8, 11, so 11% speed up, which you get it from here, okay, on scalar products, okay. Then matrix inversion, which I told you. So then matrix inversion is this algorithm, GPU algorithm. So the matrix inversion, I'm getting 19% average. On an average, I'm getting 19% speed up for the matrix inversion. These are all speed ups. The first figure is basically for my how much time, how much weightage for every component. Okay. Next is by CG step. I told you I need to solve the linear system AX equal to B by CG step. So by CG step has to be written in GPU form. So now I get 30% on an average speed up in this algorithm. Okay. Now we will understand my entire picture. So that's what now I go back to the flow chart, which you remember what I told you earlier. The CPU and GPU. Particle management is done at GPU. Internal to the particle management, I have neighbor search, I have sorting, I have insert, I have remove. All put together, I am getting almost 29% speed up. Then I have matrix operations, matrix multiplication, matrix inversion. Then I have by CG step kernel for linear solver, CSR format, compact storage, and the scalar product reduction. So all these things which I have told you already, how much speed up I am getting. Neighbor search I am getting this one 14% speed up here, 15% speed up here. Particle management 8% speed up here. Matrix inversion 19% speed up here. Scalar product 11% and 30% speed up. I am getting it from linear solver. So now system configuration, what we have used is NVIDIA Telsa. This is system configuration for your GPU. Streaming processors, size of the memory is 3 GB, clock rate is 1.15. This is my laptop, what I am using it now. Peak value is 515 G flops. Single precision peak value is 1033 G flops, gigaflops. And I am using NVIDIA Telsa is this one. Dual Intel Xeon is number of cores is 8, clock rate is 2.1. Because I told you GPU 1 and GPU 2, so we need to understand. So what we have defined is acceleration ratio. Time at CPU divided by time at GPU. This is called acceleration ratio. This will clearly tell you that as this acceleration ratio rises, the number of particles increase. Then that is a good trend. As your acceleration ratio increases, indicates your speed up. Okay, meaning your GPU is much higher than the. So TCPU is total processing time on CPU. TGPU is total processing time CPU plus GPU. Okay, so TGPU is accounted for as far as what you are doing it in CPU as well as GPU, including data transfer. It's only a data transfer between the GPU and CPU. So your acceleration ratio rises as the number of particles increases. So now using the driven cavity. Okay. Now you see the driven cavity and you see the speed up 58 point this one. I go to the next slide. This is the Manhole problem. I get the acceleration ratio something like 91.3, which is really higher. Then I go to the next slide. So the speed up distribution is this. Then so I have demonstrated all my problems where I am getting the broken dam. You see the speed up. This is the three dimensional. You see the acceleration ratio. This is the Manhole problem. So what I am saying is basically this is the broken dam problem in 2D.
Thank you very much, sir. Now I request the participants, please ask the questions one by one. The first candidate is Akansha Mehta. So please ask your question. Akansha Mehta is
Hello.
there?
Hello.
Yes.
Good morning, sir. Hello. Am I audible?
Yes, you are audible. Please ask your question.
Sir, I want to ask that which software you are using for showing simulation of particles and its neighborhood. Hello.
Oh, hello, Professor Sundar. Hello, sir. Hello.
Hello.
So please wait.
Okay, sir. Okay, sure.
Please,
Sudha sir left the meeting, sir.
Nini, just please wait. He will join. Please wait. Just wait, please. Just please wait. Hello, sir.
It got disconnected. Now
Yes,
I'll complete my presentation so that.
Akansha Mehta want to ask questions.
Yeah, wait. That's 1 minute. 1 minute.
Yes,
I will. So what I'm talking about, I wanted to tell you is, I wanted to conclude is basically the GPU computing, especially on the flow problems, on the real time, is becoming more important. We need a proper design and which algorithm. In order to do, we have to compartmentalize the entire computation. So what compartmentalize means, like I said, if you look at this, all this problem, I have a matrix linear solver, I need matrix inversion, I need neighbor search, by sorting, and remove particles, scalar product. So every part, how much speed up you are getting, then put together how much total speed up you are getting. And the speed up is basically judged through your acceleration ratio. As acceleration number of particle increases, see for example in this problem, I am taking about 1 million 10 lakhs point. My acceleration point is 81.3%. So if you look at the previous problem, Here my speed up is 62%. So as your acceleration ratio increases with the number of particles, that is a good trend. So we were able to demonstrate our this one on various problems, direct industrial problems, through which we are able to have a GPU design for the finite point set based numerical method for solving incompressible Navier-Stokes equation based on Turing's projection idea. So our concern is only on the speed up. So then, so is it fine with this? I'm closing my talk. If you have any question, please.
Okay, sir. So now the participants want to ask questions. Now the first participant is Akansha Mehta. So please ask your question.
Thank you, sir.
1 minute. I wanted to show you. I wanted to show you this one for this problem, which I have shown you the glass problem. So this we have get the speed up like for the speed up. We have taken 1 lakh. The GPU, you should just see the speed up. We get we went up to 150% speed up. With the GPU acceleration. And we have compared with different authors, how many particles we have taken, how the performance, how the efficiency. Okay. So this way we have computed, and so GPU accelerates with respect to number of particles. In 2D problem, we have taken 8,000 particles, 11 times speed up, 1 lakh particles, 62 times speed up, million particles, 82 times. Because this is very important. Increase the number of particles, your speed up. We have taken for 3D problem 5 lakhs particles, 152 times speed up. That shows the importance of GPU design and efficient coding. With this, I stop. I am open to questions.
Hello.
Hello, Akansha. Please ask your question. Akansha
Good
is there.
afternoon. Yes, sir. Yes, sir.
Please ask your question.
Good afternoon, sir. Sir, I want to ask that which software you are using for showing that short videos showing simulation of particles and
we
all.
are basically we are entire video visualization is done through Python.
Sorry.
Python.
Okay, okay, Python. Okay, thank you so much, sir.
Because Python is nicely integrated with your C++ coding.
Yes, yes, yes.
All our algorithm is on C++. So, but GPU CUDA C++, which we implemented in Python.
Okay, okay. Thank you so much, sir.
Yeah.
So let us thank Professor Sundar for his insightful and informative talk. So today morning, so we started the session a bit late than the scheduled time. So because of which we are unable to introduce Professor Sundar. So now I take this opportunity. To introduce Professor S. Sundar. He is a professor and head in the Department of Mathematics, IIT Madras. He has completed his PhD from the IIT Madras. His research areas include numerics for PDs, mathematical modeling, and numerical simulations. So Professor Sundar has been a recipient of many prestigious awards and honors, like DAD Research Ambassadors, a member of SERB DST Program Advisory Committee, a fellow of Indian Academy of Mathematical Modeling and Simulations, and many more. So he has more than 60 research papers to his credit, which are published in journals of international repute. So once again, I would like to thank Professor Sundar for sharing his valuable time and vast knowledge with us. So thanks again, sir. Thank you very much.
Thank you so much. I wish you all the best for the rest of the lectures. Thank you so much. Thank you so much. So now I leave the meeting. Thank you.
Okay, good morning to all of you. I have the great pleasure of introducing Professor V.D. Sharma, an emeritus fellow at the Department of Mathematics, IIT Bombay, and a visiting faculty member at Department of Mathematics, IIT Gandhinagar. Professor Sharma has been at IIT Bombay as a professor since 1988 and got superannuated from IIT Bombay in 2017. He has published more than 100 research articles of international repute in the area of hyperbolic system of quasi-linear partial differential equations and the associated nonlinear wave phenomena. He has supervised 16 PhD research scholars, and I was fortunate enough to be one of them. Professor Sharma is a fellow of prestigious science academies of India, namely National Academy of Sciences and Indian National Science Academy, INSA. He is also a member of the editorial board of the Indian Journal of Pure and Applied Mathematics. He was the president of Indian Society of Theoretical and Applied Mechanics, ISTAM, for the year 2010. Professor Sharma has served as a member and the chairperson of many selection committees, including Shanti Swarup Bhatnagar Award for Mathematical Sciences, Inspire Faculty Award, Shyama Prasad Mukherjee Award, Prime Minister Research Fellowship Award, etc. Professor Sharma was Institute Chair Professor for 6 years and Head of the Department for almost 7 years at IIT Bombay. He received IIT Bombay Awards for Excellence in Research in Basic Sciences in 2005 and for Excellence in Teaching in 1998, 2003 and in 2015. A Research Dissemination Award constituted by IRCC IIT Bombay for the year 2015 was conferred on the monograph Quasi-Linear Hyperbolic Systems, Compressible Flows and Waves, authored by Professor Sharma. He received the C.L. Chandana Mathematics Award from the Canadian World Education Foundation for distinguished and outstanding contributions to mathematics, research and teaching in 1999 and M.S. Award for research in theoretical sciences from the University Grants Commission, UGC, Government of India in 2001. Please join me in welcoming Professor V.D. Sharma, who is going to talk about some aspects of ordinary differential equations. I request Professor Sharma to start his presentation. Thank you, sir. You can start your presentation. Your another device is open. Sir, hello. Please, sir, unmute your microphone. Hello.
Sir, left the meeting, sir. Maybe it is why.
Yeah, we are trying to write. Professor Sharma will join very shortly. Due to some network problem, he got disconnected. Probably he has joined again.
Hello, are you there?
echo in your voice. Probably you have opened the two devices. Yeah, correct. Now I think so please unmute your microphones.
Yes. Are you able to hear me?
Yes, sir.
Okay, all right. So, thank you, Zafar, for a very kind introduction. Now, I have two lectures. So, in this lecture, I will talk about ordinary differential equations. And in the next lecture, I will talk about first order quasi-linear partial differential equations, right? Which govern the phenomenon of nonlinear rates. And in fact, it's all pervading. But anyway, I will talk about this topic tomorrow. Today, I will talk about the basic ODEs. This I have noticed that you see, many young fellows, those who are doing masters or who are doing postdoctoral fellowship somewhere, or those who are applicants for a faculty position elsewhere, and those who are the young faculties in various colleges, I have noticed that there is a confusion about the notion of a solution. For example, when we talk about this function, say y is equal to, are you able to see it? Y is equal to some function of x, let me write 1 by x.
No, sir, your video is not present.
Is it visible? Hello, on the screen?
No, sir.
Oh, really?
A bit okay, but clarity.
You cannot see anything on the screen? Hello?
Yes, sir. I guess we can see your screen.
You can see your screen, but actually your writing board is not visible.
Really? So can you see it on the screen?
Your screen is visible, sir, but your writing board is not visible.
I think document camera is functional and
It's not being shared.
that's cool.
Sir, you have to share it, sir.
Yeah, actually, we are trying to connect it. Please wait for some time. Within 1 or 2 minutes, he will connect.
I hope.
Yeah. Your board is visible, but you have to open a little bit.
Just one. Is it all right? Are you able to see it?
Yes, sir. It is visible.
Oh, fine. So what I said that in this lecture I will talk about
Please
the
make
basic.
please make it in full of screen. You have to click on this arrow.
Yes.
Yes,
Is,
sir.
is it all right?
Yes, sir. It is all right.
Okay. So you see, when I talk about this function 1 by x, its domain, obviously its domain is r minus 0, right? Is it, are you able to hear me and whether it is visible, whatever I am writing here on the paper?
Yeah, yes, sir. It is visible and audible as well.
All right. So what I say that there is a difference between a function and the solution. I mean a function which represents a solution. For example, y is equal to 1 by x. If I treat this as a function, its domain is r minus 0, right? I mean at 0 it is not defined, so its domain of this function is r minus 0. But one can see that it also satisfies this differential equation, right? Y is equal to 1 by x. Now as a solution of this differential equation, I see 1 by x as a solution of this differential equation. So whether somebody would be able to tell me what is the domain of the solution? If 1 by x is regarded as a function, its domain is this. But 1 by x, one can quickly see that it satisfies the differential equation identically, so this is also a solution of it. And if I ask that what is the domain of the solution of this differential equation? Yes? Whether anybody, I mean young teacher or young postdoctoral fellow, whether would be able to answer this question? What is the domain of the solution of this differential equation which I have written 1 by x? Hello?
R minus 0.
Why can't be 0?
This is not correct. This is not correct. So you see, this is the confusion. This is the confusion amongst the, I mean, young fellows.
Real numbers.
No. So let me explain. What is the definition of a solution? Solution means a function. You see, when I say that it is defined on some interval, okay? The differential equation is defined on some interval, and when I say that phi x is a solution of this, it means if I write this differential equation as y as a function of x and y, by the solution of this means this function is differentiable at every point of the interval and it satisfies this equation identically. This is the meaning, right? On the whole of interval. So the solution of a differential equation is an interval. The solution of the differential equation is an interval. So the question is this, that what is the solution, what is the largest interval on which the solution exists? Obviously r minus 0, no, it cannot be. Because if I take 0, any interval containing 0, say minus 1 to plus 1, is it the domain of the solution? You see, not only function, now I need that function should be continuous, not only continuous, it should be differentiable, not only differentiable, the derivative should also be continuous. So do you think that any interval containing 0 can be the domain of the solution of this differential equation? Hello?
Sir, minus infinity to something a greater a and then a2 into we will exclude the
Zero to
domain.
infinity or minus infinity to 0.
Yes, this is correct. So the largest interval could be either this.
Union 0 to infinity.
No, that's not an interval. What is the definition of an interval? The definition, you see, this is union. I mean, it's not an interval. What is an interval? If A and B are any 2 points in the interval, then all those numbers between A and B should belong to it. And therefore, minus 1 to 1, oh, it's not an interval because you see 0. At 0, function is not defined, it's not continuous. I mean, we cannot talk about the derivative. Right? And therefore, the largest interval on which the solution is defined is this or this. Or this. the solution. You say once you are given an initial condition, that initial condition fixes the interval. For example, if the condition is specified, say at y at 1 is equal to 1, then the interval is different. It forces the interval to be this, not this. If the initial condition is y minus 1 is equal to, right? This has to be, let's say, some number k, then it means it is defined on the negative x-axis, therefore this has to be the interval. No interval containing 0 can be the domain of the solution function. So there is a difference. There is a difference between the function and the function which represents a solution of a differential equation. Because here we want this to be differentiable. We want no interval containing 0, right? You will find that at no interval, right, containing 0, the function is not even continuous. What to say of its differentiability? Therefore, this cannot be the domain. Minus infinity to plus infinity minus r is not an interval, right? So you see, at higher level we know that domain has to be a connected set. The domain of a differential equation has to be a connected set. What is domain? Domain is an open connected set. So an interval is connected here. This minus infinity, 0 to infinity, union of this is not a connected set. It's not connected. So it is very clear, first of all, to understand what is the difference between an ordinary function and a function which represents solution of a differential equation. This is most important. This is most important. So now we proceed further. You see, if x, y dash plus, say, let me write y is equal to 1, okay? Now, what about x is equal to 0? It is a singularity of the differential equation. What is x is equal to 0? It is a singularity. So here obviously x should be different from 0. It is understood, even if it is not mentioned, it is clear, because when x is equal to 0, it is no more a differential equation, it is just an algebraic expression, y is equal to 1, right? Therefore, x not equal to 0 means x may be positive, x may be negative. Depending on the initial condition, it will be decided what is the interval. So if you look at it, the standard form of a linear equation, I am talking about the linear equation, P of x, y is equal to Q of x. X belongs to some interval. Remember, this is the domain of this differential equation. Now, if P and Q, they are continuous functions, it's a very standard theorem, the most basic theorem, that if P and Q, they are continuous functions on this interval, then this differential equation satisfying some initial condition, say yx naught is equal to y naught, it has a unique solution on that interval. What it says, if P and Q, if they are continuous, say on this interval, then the differential equation has a solution which is of class C1, not only continuous, but its derivative as well as derivative is also continuous. This is the most big, but what happens if P and Q, they cease to be continuous? For example here, and you see the proof of this theorem is, contained in this expression, that is e to the power minus p dx, a very standard formula, that is q e to the power minus p dx dx. A very standard formula. In the derivation of this, the proof of this theorem is contained, which says that if P and Q, they are continuous on this interval, then the initial value problem has a unique solution on the whole of that interval. That's very important. On the whole of that interval. This solution exists on the whole of that interval, and it is of class C1. Now what happens? What happens when this is multiplied by, say, x? What is P here in this particular example? Here P is your 1 by x, and here Q is your, P is 1 by x, and Q is also 1 by x. So the question,
At x equal to 0, that is the point of discontinuity for px and qx.
for P and, right, okay. So what can be said about the solution? This is my question.
So
If P and Q they exhibit a singularity at say x is equal to x naught, my question is this: what can be said about the solution of the differential equation at x is equal to x naught?
Either minus infinity to x naught, yeah, x naught to infinity.
Pardon?
Either minus infinity to x naught, yeah, x naught to infinity.
That is right. My question is this: whether the solution will exhibit a discontinuity at x naught. Do you want to say this thing that it will exhibit a discontinuity?
May or may not.
Pardon?
May or may not.
May or may not. What is that which ensures that yes, may or may not?
The solution may be continuous at x naught. Maybe.
And maybe discontinuous also, right?
Yes.
But it can be continuous, it can be discontinuous, correct?
Yes, sir.
Why is it so?
Sorry, sir.
Why? What is the reason? All right, the answer is correct, but reasoning should be clear. So think about the reasoning. We will talk about it a little later.
So because domain of the differential equation doesn't guarantee the solution's domain, that where it should be continuous or discontinuous.
The domain of the solution, yes.
Domain of the differential equation doesn't guarantee the domain of the solution, that whether it is going to be continuous or discontinuous at that same point, because the solution can be of different functions. That's why.
So I just wanted to know what is the reason behind it. Is there any theorem which states like this?
Existence theorem?
What it says? Existence theorem says that if P and Q are
continuous and
if P and Q are continuous, then the solution is of class C1 and it exists on the whole of I. On the whole of, this is the statement of the theorem.
Yes, sir.
So all right, you think about it, that why is it so? Perhaps, yes, your answer is correct, that the solution may or may not exhibit a discontinuity at x. So this is a very important thing, you see. The solution may or may not exhibit a discontinuity at x is equal to x. If x naught is a singularity of this function, you think about the reasoning, and towards the end, perhaps, yes, again we will come to this point a little later. All right. Let us take yes, say for example, let's consider this differential equation, say x y dash is equal to 2y. X y dash is equal to 2y. Satisfying some initial condition. Say, let's take some convenient condition, which say, let's take, say, y0 is equal to 0. Y0 is equal to 0. X y dash is equal to 2y, y0 is equal to 0. At 0, it is defined as 0. So, if you look at it, what can be said about the existence?
Sir, please move it on the right side of your. Sir.
Like this?
Yes, yes, sir.
Okay, all right. So, what can be said about this initial value problem? Are you sure if I have shifted it towards the right, can you see it better?
Yeah, it is much better.
Okay, all right, good. So, if you talk about, yes, this initial value problem, the question is, can we say that the solution exists? Hello?
Yes, sir.
can exist.
Where? Whether?
It is much better, sir. This pen is much better.
All right. Whether the solution exists? If yes, what is the domain?
Is it whole R, sir?
Again, you see, same mistake. It is defined at 0. it is defined at 0, but x is equal to 0 is a discontinuity of the differential equation.
Right.
So what can be said? I mean, it is very clear that solutions are undefined on the real line, right, at x is equal to 0, except perhaps 0, 0. Because if you look at it, y dash is your 2y upon x, right?
Your question is not visible, sir.
It's not visible.
Sir, actually the initial data is not visible.
Is it clear? Hello? Now?
Now it is much clear, sir. Initially it was not visible. The initial
Okay.
data was not visible.
All right. Yes. So it is very clear that the domain, in fact, it could be, yes, we can talk about x greater than 0 or x less than 0. No solution can cross the y-axis, right? Except perhaps at 0, 0. Except perhaps at 0, 0. Because at 0, 0, you can see that this equation is satisfied identically, and of course, it satisfies the initial condition as well. But quickly you can see that y is equal to c of x square. Y is equal to c of x square, right? Where c is an arbitrary constant, quickly follows using the separation of variable method that this is the solution, where c is an arbitrary constant. So, in fact, there are infinite number of solutions for c positive. For c positive, there are infinite number of solutions, and similarly for C negative, there are infinite number of solutions as a matter of fact, because C is quite arbitrary.
So solution will be e की power x square, no?
Why? It is y dash upon y is 2 by x. So ln of
Okay. Sorry. 2y.
So this is the solution. This is solution.
Yeah.
Okay. Now obviously this is, so you see there are infinite number of solutions. In addition, if you look, y is equal to 0 is also a solution. Y is equal to 0 is also a solution. Y satisfies it identically. Moreover, it is very clear that when c is equal to 0, right, we get y equal to 0, which satisfies this initial condition. So there are infinite number of solutions, including y equal to 0. Right? Now you see, it is something which is very interesting. Suppose the initial condition is specified. Suppose the initial condition is specified at 1. y1 is equal to 1. What can be said about the solution? Suppose instead of this, right? So, or you think of a solution which passes through 1, 1. Which passes through 1, 1. 1, 1 is this point. Okay. So what can be said about such a solution? Is it unique?
Yes, sir. Y is equal to x.
Is it unique? Whether the solution is unique? Hello?
Yes, sir. It is unique. Yes, sir. Because constant value, we are getting a constant value.
So
At a particular solution.
it is unique on which interval?
Sir, from
0 to infinity.
0 to infinity.
All right. What happens on the negative side?
It again shows the same behavior.
No, it doesn't. It doesn't show the same behavior. In fact, you see, there are infinite number of solutions because here y is equal to, you see, y is equal to cx square. As a matter of fact, there are infinite number of solutions.
Yes.
There are infinite number of solutions. A solution passing through 1, 1, you see, it is unique only in a, yes, in this part, but we see that after this point on the left, it loses its uniqueness. It loses its uniqueness. You see, such a, I mean, so equations which involve discontinuities or singularities, they are really very difficult. They are very difficult. So in fact, you can see a unique solution, in fact, it branches out into infinite number of solutions, right, on the left hand side. As a matter of fact, it has infinite number of solutions, and similarly the other way. If suppose the solution passes through this point, say it is -1, 1, it is -1, 1, then this solution is unique, but after that uniqueness get lost. You see, the solution branches out into infinite number of solutions on the right. And therefore, it is a very important example, although very linear case. It is a linear equation, right? But it gives us an idea that solution, in fact, if it is valid in the neighborhood of that point, outside that neighborhood, in fact, nothing can be said about the solution. Nothing can be said. For linear equations, perhaps it is possible to say, but for nonlinear equations, nothing can be said. We really do not know. Solution may exist, solution may not exist uniquely. A unique solution may bifurcate, right? May branch out into infinite number of solutions beyond that reason. So in fact, you can see that here, yx, as a matter of fact, this is your x square when x is less than or equal to 0, right? X square when, in this case, yes, it is greater than or equal to 0, and cx square in this, right, when x is greater than or equal to 0, in this case, and cx square when x is less than 0. So you can see that solution, in fact, not only continuous but differentiable at this point. You look at it, it is very clear, but the uniqueness gets lost after this point on the left. So this is a very important thing which is to be kept in mind, that once the singularities appear, one can predict just by looking at that the solution, in fact, is not very simple. But it is very clear that x is equal to 0 is a singularity, then the solution cannot exhibit any other singularity, no matter which initial condition you take, right? Solution will always, but this doesn't happen. This doesn't happen for nonlinear equations. For example, let us take this example. Say y prime is, say, y square, a very simple function. And yes, let's take that y0 is equal to 1. Consider this initial value problem. This equation is nonlinear, right? Now look at the function which appears on the right hand side. It's a very nice function, differentiable any number of times in the whole xy plane at every point, right? But remember, it is not possible to solve every nonlinear differential equation, and that's why there is a result, existence uniqueness result, which says something which is very important, that if those conditions are satisfied, then we can say that wherever the solution exists in the neighborhood of this point x0, y0, here x0 is 0, y0 is 1, outside this neighborhood, in fact, nothing can be said. But in this example, of course, it is very simple, so we can say something, but it is something very interesting. So what is the solution? You can see quickly that solution satisfying it should be what? 1 minus x. Am I right? Because when x is equal to 0, y0 is equal to 1, it satisfies the initial condition, and one can quickly see that it satisfies the differential equation identical. Is that right? Hello?
Sir.
Yes, sir.
So what do we notice? Can you tell me what is the domain of the solution of this function?
Minus infinity to 1.
Minus infinity to 1 and 1.
No, that's wrong. You see, don't accept. This cannot cross this line. That's all.
R minus 1.
No, this is wrong. No, again, same mistake. You see, I spent nearly 7 minutes in explaining that nothing r minus 0, because r minus 0 is not an interval. R minus 0, yes.
1 to infinity, and if we want to take a biggest interval,
Yes.
that's minus infinity to either 1 or 1 to infinity, or we can't take unique, no?
The again answer is not correct. Look at the initial condition. This will force that what should be the interval.
So interval will be
one
minus
comma infinity.
to 1.
Yes, it should be minus infinity to 1.
So
That's
the
all.
boundary condition,
Boundary condition is at
boundary
0.
condition satisfies that interval.
When x approaches 1, right? When x approaches 1 from left, what happens? Y goes to infinity. Y goes to infinity. This is the graph of this function. Is that right? Hello?
Yes, sir.
That's all. So this is the domain. The domain is minus infinity to 1. Look here. The domain, so what I want to say, if the differential equation is non-linear, it is very, very difficult to predict the interval of validity of the solution. That what is the interval? But here, of course, it is so simple. We can look, you see, once the solution is known, but non-linear equations in general, they are not solvable. But by some analytical method, if you are able to solve a simple equation, even then it is difficult to find out that what is the interval on which the solution is valid. Here, of course, it is very clear that this is the interval. But it is very surprising, you see. Such a nice function which is differentiable everywhere, and there is no clue that x is equal to 1 in what way it is important. There is no clue about it. At x is equal to 1, the function, you see, the solution becomes unbounded. So if I consider only on this, or for x greater than 0, for example, then I find that the solution breaks down after a finite running length. So in fact, we will talk about this in the context of partial differential equations. This is extremely important, you see. And moreover, the more disturbing thing is this: x is equal to 1 is a singularity of this differential equation now. But by looking at it, nothing can be said that in what way this x is equal to 1 is important. Because this does not depend on the function f. Here f is your y square. The form of function f on the right hand side does not indicate that x is equal to 1 is important in any way. It is very, very in contrast to the linear differential equation. In linear differential equation, we know that if p and q, you see, they decide. If p and q, they are continuous, we know that the solution has to be continuous on the whole of I. If p and q, they exhibit a discontinuity at x is equal to x naught, the solution at x is equal to x naught may or may not exhibit a discontinuity, but we know that no matter what initial condition is this, right? All the time the singularity will not move, but here the singularity can move, because if I take the initial condition, y0 is equal to say 2. Okay, at x is equal to 0, if it is 2, can you quickly tell me what is the solution now? Hello? Hello, is it correct? Just verify, because at x is equal to 0, y is equal to 2, it satisfies this initial condition, and you can see quickly, you see, variable separable method gives you the solution. And here, what do you get? In fact, minus 1 upon y, as a matter of fact, minus 1 upon y is equal to x plus constant. So at y is equal to minus 1 upon x plus c. Now you can see that when x is equal to 0, y is equal to 2. So you get so correct. This is the solution, correct solution. But you can see that now the singularity has moved. Singularity is 1 by 2 now. Look here. The singularity has it is 1 by 2. With this initial condition, this is in contrast to the linear differential equations, which say that if x naught is a discontinuity, no matter which, first of all, this discontinuity will be exhibited by this function which appears on the right. Because what is f here? Transposing this to the right, we get q minus py. This is the function on the right. And you can see that p and q, they are discontinuous at x is equal to x naught. So by looking at it qualitatively, we can say immediately that if the solution exhibits a discontinuity, this point has to be x0 only, no other point. But here, there is no indication from where this 1 comes. X is equal to 1 is a singularity. But if I take this initial condition, you can see that x is equal to half is the singularity, as a matter of fact. So this is another disturbing feature of nonlinear equations, that the singularities of the initial value problem, they move about, right? They move about. And therefore, and you see one more interesting thing, you see. For first order differential equation, we have seen that the solution, this P and Q, they are functions of x, and of course, P is a function of x, and this initial condition, of course, that y at x naught is equal to y naught. The solution is always explicit form of the solution. Explicit means this y can be expressed as a function of x only. Y can be expressed solely as a function of the independent variable. The explicit form of the solution. In fact, the derivation of the general form of this formula, such a formula we don't have. You see, this is the formula that y is minus p dx and c plus, what do you get? E to the power, this is minus, so this is plus e to the power p dx, and this is q dx. General formula. It says that the solution is explicit, is a function of x, right? So for linear equations, the solution is always explicit. And in fact, any particular solution can be obtained from this. Any particular solution can be obtained from this by specifying some value to c. But this is not possible for this. Just we have seen that y dash is equal to y square and y0 is equal to 1. What is the, for example, the general solution, that is minus 1 by y, yes, what do you get? X plus c. So y is equal to 1 upon, say, let me write c, so say this is c minus x, is it all right? This is the general solution, c minus x, okay? Now you can see that if I write, say, y0 is equal to 0, okay? If I write the differential equation, say y0, now you can see the general solution. All right, forget this condition. This is a general solution. Now, if you look at this differential equation, y equal to 0 is also a solution. It satisfies this identically. But this particular solution cannot be obtained from this general solution by specifying any value to c. Yes or no? Hello?
Yes, sir. Nothing can be.
Yes, this cannot be. So it is very important to understand that the notion of a general solution is relevant only for linear equations, not for nonlinear equations. Because for nonlinear equations, there are other solutions which cannot be obtained from this solution which involves an arbitrary constant. But for linear equations, in contrast, every solution of this can be obtained from here by specifying values to this arbitrary constant. So this particular kind of behavior, yes, is not present for nonlinear equation. This simple example illustrates this idea. Is it all right? Hello? This is something which is very important.
Yes, sir.
And number two, the explicit form of the solution. It is very clear. Linear equations always give you an explicit form of the solution, right? But for nonlinear equations, even, you see, it's very simple. For example, if I say that x plus y, y dash, this is equal to 0. Look here, the simplest first order nonlinear equation. Look at this. This is the simplest nonlinear equation one can think of. What is the solution to this? X square plus y square is equal to constant. Is that right? Hello?
Yes, sir.
So, whether the solution is explicit?
No, sir.
It's not. So even a very simple differential equation, in fact, the solution is in implicit form, right? The solution, it is some function of x and y. Some function of x and y, this is equal to some constant, right?
Yes,
this is the, so it is very important that every solution of a linear equation is in explicit form, but the solution of a nonlinear equation in general is always implicit, Now this implicit form, how to get the solution? The solution can be obtained, yes, y is equal to, what is that theorem which tells us, yes, if these conditions are satisfied, then perhaps we can get a function representing a solution to this differential equation. This is called implicit function theorem. Hello?
Yes, sir.
But for implicit function theorem, there are some conditions. What are those? Number one.
Excuse me, sir.
Yes, please. Yes.
Solution of this equation, x square plus y square plus z square, can be written as y is equal to plus minus c square minus x square of square root. Then what is the explanation?
No, there are two solutions, not a single equation, you see. That is all right. Here you are able to, what you want to say, is it explicit? Hello?
Yes,
Is
sir.
it-
Yes, sir.
No, there are two solutions. Y is equal to with plus sign and y is equal to with minus sign. There are two solutions. Hello?
Yes, sir.
Okay, sir.
This represents, you see, x square plus y square is this. Can you tell me what is the solution of this? Hello? You see, there are several functions which satisfy this relation. It is a relation. It does not represent a function. It is a relation. Okay? It is a relation. It represents, as a matter of fact, there are several functions. There are several functions which satisfy it. For example, I can take this function phi1. What is that phi1? I can take this as c square minus x square, and I can take this as minus c square minus x square. And yes, this lies, or this is on the interval minus c less than or equal to x less than or equal to c. Okay? This is on the interval minus c less than or equal to x less than or equal to c. There could be, yes, some other function I can write. Let me take this part, this is your minus c, this is your plus c. I can write, so here, this part, what is this part? That is minus square, this is your square root of c square minus x square on this interval minus c less than or equal to x less than or equal to 0, and this part, yes, I can write minus square root of c square minus x square, and this I can write 0 less than x less than or equal to c. In fact, I can write infinite number of functions, you see. I can write in this way, say I will write that this is, say, on this interval it is minus c by 2, this is your c by 2. I take this branch, look here, I take this branch, so let me say this is your b1, this branch is b1, this branch is b2, okay, and this branch in fact is b3, this is b3. I take this as, right, b1, b2, b3 on these subjective intervals. So in fact, a sequence, large, infinite number of functions, they satisfy it. Is that right? Hello?
Yes, sir. This is not an explicit solution because there are number of solutions included in this.
Right. So it means this is an implicit form, right? It is an implicit form. And what is the solution? Can you tell me out of these? Can you tell me which is the solution?
Sir,
What about 5? Is it a solution?
5-1.
Hello?
5 will be the solution.
5-1 is a solution? Hello?
Yes, sir.
sir,
So phi2 is the solution.
5-2 is the solution.
Even 5-2 is not a solution. What is the mistake? Tell me.
yes, we are including the c, neighborhood of c.
Because here y dash is not defined. Here y dash is not defined, so it will not. So it has to be an interval. You know, at these points, y dash becomes infinity,
Yes, sir.
and therefore the solution has to be an open interval from open interval minus c.
Minus c2 plus c.
So what I want to say, there are infinite number of functions which satisfy this relation, but all of them, they need not be the solution, in fact. So what I want to say, that solution in general is in implicit form, because you see here it is a quadratic form of f, that's why we are able to solve it. Had it been cubic or quartic, it would have been very difficult to find an expression for y. Yes or no? Hello?
Yes, sir.
So this is a major difference. This is a major difference between linear and non-linear. For linear equations, the solution is always explicit, because this idea we will discuss with partial differential equations as well. So in the tomorrow's lecture, I will talk about the explicit and implicit form of the solutions. And we will see that what kind of problems do we face. So here it is clear that large number of, so this is a very important difference between them, that nonlinear equations in general, the solution is never explicit, and therefore it is very, very difficult to find an explicit solution, and moreover, we do not know what is the integral of it. Because you see, had it been a cubic or quadratic, even it is difficult to find that function, and even if the function is known, we really do not know what is the integral on which the solution is valid. So you see, these are the real difficulties, and just for this, now there is a, important result, because it was seen that yes, there are, say for example, let's take this y to the power say 2 by 3, a simple example, where so what can be said about this differential equation? Hello?
Sir, why?
Sir, it's not visible.
Oh, sorry. It's not visible?
No, sir, it's visible.
So this is the differential equation. Y prime is equal to 3 multiplied by y to the power 2 by 3. So can we say that the existence is, yes, what is that which ensures the existence?
By Picard theorem, this is a continuous function.
Very good, nice. It is a continuous function. But what about its differentiability? Hello?
Y is equal to 0
There is a problem. Y is equal to 0, there is a problem. Not even Lipschitz, because differentiability is a sufficient condition, a stronger condition, right? But these are sufficient conditions, of course. But differentiability is a stronger condition. Lipschitz is a weaker, but Lipschitz condition is also not satisfied in any reason where y equal to 0, right? Which contains y equal to 0. So what is the general solution? The general solution, I can write x plus c whole cube. Just verify, is it all right? C is an arbitrary constant?
Yes, sir.
Yes.
Yes, sir.
All right. So, very right. So, if I take the initial condition y0 is equal to 0, suppose this is the initial condition, obviously, what can be said about the solution? Solution exists. Will it be unique?
No.
So, how many solutions do we anticipate?
So please repeat.
This is an initial value problem, right? This is an initial value problem, correct?
Yes.
This is an initial value problem. The question is this, whether this, it is very clear because the function is continuous, right, in a neighborhood of 0, 0,
Yes.
correct? The question is this, whether it admits a unique solution.
No, it does not.
No.
It is not. So can you identify some of the solutions?
Y equal to 0 is also solution, which is not dependent on y equal to x cube.
The solution, y is equal to, of course, from here what you get, c is equal to y is equal to x
Y
cube.
equal to x cube, yes.
X cube. What about, is there any other solution?
Sir,
Yes.
What is that?
Some x plus alpha we define y of x is equal to 0 if x between minus infinity to some alpha, minus infinity to some alpha,
Okay, minus right.
and then x plus alpha, x plus a,
This is very right.
x minus,
Yes, for x greater than k, right? So in fact, you see, it contains infinite number of solutions. As a matter of fact, we can have, large number of solutions. So why this problem? Because the conditions, existence uniqueness conditions, right, are not satisfied. If the existence uniqueness conditions, what they say, that if the function which appears on the right hand side, if it is continuous in some rectangle about 0, 0. By the way, why do we take rectangle? Hello? Why do we take rectangle? No, it's very clear. You see this. It says that y dash is equal to f of xy, y at x naught is equal to y naught. This initial value problem, right, has a unique solution in this rectangle, say for R that is x minus x naught, say less than or equal to a, y minus y naught less than or equal to b, right? This initial value problem has a unique solution in this, and the solution exists in this interval. You remember, this is less than or equal to h, and what is h? It is the minimum of these two numbers, a and b by n. Hello? The existence uniqueness theorem, this is a very, very important result, you see. At 0, 0, suppose if the function is defined at some point, right? In the neighborhood of that, if we can, yes, have this rectangle where a and b, I mean, there are positive numbers. This existence uniqueness theorem says that this initial value problem will have a unique solution in this interval. What is the meaning of this theorem? It is very clear. What is m here? M is nothing but the maximum of this function over this region R. This is the region R. What it means? The theorem, in fact, what is y dash? Y dash is the slope of this function, right? Y dash is the slope of the solution function. So y dash is nothing but your f. And the maximum value of f is n. It means this slope, right? So there are two possibilities. Either the solution is confined just 1 minute. Yes. So either this is the situation, because this is your y minus y naught is equal to m into x minus x naught. This is your y minus y naught is equal to minus m x minus x naught. That is, solution is confined, yes, in this region. This is the meaning. This is the meaning that m is the maximum of f, so the solution has to be like this. It lies in this region, right? This is the, I mean, it should be confined between these two lines of slope n and minus n. This is the whole idea. In the neighborhood of this, we can think of a rectangle, and so we can predict that in this neighborhood, the solution exists and it is unique. This is the statement of this, right? You can see that if this is your, say, b, and this distance is your a, so this is the case, that is b by n, the slope is given. So here you get b by a in one case. So there are two possibilities, that these two lines can leave the rectangle, yes, either here, or they can leave like this, right? These lines can leave the upper edge here, lower edge, or this vertical sides. There are only two possibilities. Under these two possibilities, we get two different conditions, namely, what are those conditions? That b by m is less than a, b by m is greater than a, and that's why you see it is the minimum of these two numbers. H is the minimum of these two numbers. Okay, this is your b by n, this is the interval h, this is the interval h. So h is the minimum of a, this whole is distance from here to here is a, and this is b by m. So h is the minimum of a and b by m. So this theorem, in fact, but remember that these are only sufficient conditions. Sufficient conditions means, yes, you might have an initial value problem where these conditions are violated, right? The function, I mean, doesn't satisfy these conditions, but even then the solution might exist. A unique solution might exist. There are examples in the literature, only sufficient conditions. So,
in the above solution, k will be greater than 0.
Pardon? A and B, they are positive numbers. A and B are positive numbers.
No, sir. Sir, in the solution of above question, sir, y is equal to x plus c whole cube. The interval you have taken minus infinity to k. So, k should be greater than 0, or it can be any constant.
You are talking about this?
Yes, sir. Yes, sir.
Oh, yeah. In fact, you see, this is a singularity at this, so really does. So k is any constant, you see. For less than k, it is like this. For greater than k, it is like this.
Okay.
So I think the time is up. It is 12:40. I close here, but tomorrow I will be talking about partial differential equations, where some of these notions you will find that they are very important and most basic. we'll talk about explicit and implicit solutions of a hyperbolic, the simplest possible of a hyperbolic differential equation of first order. We will talk about it. But these notions will be important, right? So, yes, any question you would like to ask?
Yeah, let us ask any question. If there is any question, please ask one by one.
Sir, which book should we prefer to read such type of deep concept?
Oh yes. You see, there is a book by Coddington. It's a very good book, you see. Coddington.
Coddington.
Okay. You see, there are two books. One is written by Coddington and Levinson. It's a very difficult book. Don't read it. I mean, it is for a specialist. But those who are associated with the teaching of undergraduate mathematics, for them, Coddington is a very good book.
Sir, excuse me, what is the name of this book, please?
Coddington, an introduction to ordinary differential equations. Perhaps I don't remember the idea, but it's a very famous book. You see, Coddington, CEO.
E.A. Coddington, I think it's.
Perhaps E. Coddington.
E.A. Coddington.
Correct, very correct.
Sir, with the kind permission of the Honorable Coordinator, sir, I have a query. Sir, may I please?
Yes.
Okay, sir, thank you very much. Sir, basically I am a core business graduate, a chartered accountant by profession. But actually, nowadays the problem is happening up for me. In the industry, already we are going for the machine learning, artificial intelligence, that sort of thing. So that's why the application of mathematics and statistics is being pretty much, necessary for us over there in England. Okay. So that's why, sir, the problem, is being faced by me, particularly for making actually a financial decision and go for the auditing procedure as well. So on that point of view, sir, would you please be kind to provide me some very basic book to begin from and to learn the ordinary differential equation very well, particularly in the field of business mathematics? Thank you very much, sir.
You see, in the recent past, many books have been written, which exhibit large number of applications. I can, yes, there is. You just write an email to me. I will write to you back. Mentioning some of very good books which talk about mathematical models in finances. In engineering, in physics. Large number of.
For me, the problem is happening up there. Many of my colleagues, they are simply working by installing the packages, in Python and R. But one of the very, great Indian mathematician, Honorable Professor Dr. C.R. Rao, once told that your data is talking to you. Please try to listen to it. Okay, so I do not need only the number, but why this number is coming. The intuition behind that number. That's why, sir, I want to brush up my basic very well. I hope I have been able to make you understood what my problem is. Right, sir?
Yes. Very good.
Thank you very much, sir. So definitely I will email you today.
You see, moreover, the thing is this, for a mathematician's job is to look at the problem, because mathematicians, they do not develop a mathematical model. I don't think any mathematician can do it. Part is done by engineers, physicists, scientists, right, biologists. These are the people who provide a model. Mathematician's job is to look at this problem and to see whether the solution exists or not. If it exists, yes, whether it is unique or not. And if the solution ceases to be unique, it cannot describe any physical situation. So again, it goes back to the people, those who have modeled it, they modify it, and again it comes to mathematician. It is like this, you see. Modeling part is done by other people. Yes.
Okay, any other question? Okay, if there is no question, let us thank Professor Sharma for this insightful session.
Hello, sir.
Yeah.
Yes, I have
Please
some
go ahead.
questions.
You would like to ask a question?
Hello, sir.
Yes.
Yeah, please go ahead.
What is the relation between the domain of differential equation and solution and domain of solution?
I mentioned about it, that I gave an example, 1 upon x. So you are very right, its domain is r minus 0. R minus 0. That is all real numbers except 0. It is the domain of this function. But a function which satisfies the differential equation, right? The question is, what will be its domain? So you go back to the definition of the solution. This definition of the solution is this, that it is a function which satisfies the differential equation identically. That is, function is not only continuous, it is differentiable and satisfies the differential equation identically on that interval, at every point of that interval. So here if we say that minus infinity to plus infinity, yes, definitely, I mean it's not an interval. It is not minus 0, it is not an interval. And therefore, the largest interval, because no solution can cross the line, I mean, you have one, it should be very clear. That is, no interval which contains 0 can be the domain of the solution function. It should be either minus infinity to 0 or 0 to infinity. Hello, yes.
Means domain of the solution is subset of domain of the differential equation.
Okay, what do you say?
The domain of the solution of a differential equation.
Right.
Subset of the domain of differential equation.
No, Zafar, what is he saying? I am unable to understand what, I mean, because voice is not very...
Your voice is breaking. Actually, we are not able to get it, your question.
Sir, I wanted to ask that according to your example, the domain of solution was a subset of domain of differential equation. So is it always the case that domain of solution will always be the subset of domain of differential equation? Or can it be superset also?
No, even what is the domain? The domain is either x greater than 0 or x less than 0. If you look at the differential equation, because x is equal to 0, I mean the first term, if y dash is finite.
That was a specific example, right? In a different case or in a different example, can we have that domain of solution is larger than domain of...
No. You see, at most, the domain of the solution can be the interval on which the differential equation is defined, at most. But in general, it is a subset of that. Hello? For linear equations, if the domain is I, then the solution exists uniquely on the whole of that I, which is not true for nonlinear equations. For nonlinear equations, you get simply a neighborhood of that point. Okay?
Okay, sir.
Okay. Any other question?
I have one question.
Okay.
Sir, actually here you consider the first order equation y dash is equal to 3y power 2 by 3. Suppose if it's a higher order or if a differential equation is given in a coupled non-linear equation.
Yes.
Is it possible to check this kind of solution is exist or not?
You're very right. Coupled for, you see, you have a distance uniqueness theorem because higher order equations, they can be expressed as a system of first order, right?
Okay.
Higher order equations can be expressed as a system of first order equations. So first order equations play a very important role, right? The same condition, Lipschitz condition, I mean, Peano's existence uniqueness conditions can be translated to systems as well.
Because this question is related to, suppose if you take a some realistic situation, the differential equation will not be all, not of this type of. You will get a complex differential equation.
No, that's right. We are talking about real, I mean, very special case, of course. Complex situation is much more, I mean,
in such cases, it is difficult to check whether the solution exists or not. Then we cannot think on this. We proceed for the numerical methods and we proceed.
No, you see, for numerical method, I mean, all useless, you see, unless you know whether the solution exists or not. If you are not sure that the solution exists and is unique, there is no point in proceeding for the numerical solution. Because the numerical solution, it's quite possible that it may converge to a wrong solution altogether. So first of all, you should be sure that the initial value problem has a unique solution. And if you are, the theory will tell you whether it has a unique solution or not. If it has a unique solution, then you should go ahead for numerical solutions. Otherwise, without checking for the uniqueness, if you go for numerical solution, you may end up with the wrong result. You might get something because there is no way to justify or verify whether it is really a solution or not. So many the problems they are of this kind. Given a system, first of all, you should know whether the solution exists and is unique or not, because that is the test of the model itself.
Okay.
Yes.
Okay, any other question?
Thank you, sir.
All right. Okay.
Okay, if there is no question, let us thank the Professor Sharma for this insightful and eye-opener lecture. Thank you very much, sir.
All right.
Okay, so you may leave for today's session. Tomorrow we will meet at 10 a.m. in the morning. Thank you very much.
Thank you, Jafar, and thanks everybody.
Thank you, sir.
Thank you, sir.
All right.
Thank you, sir.
Okay.
Thank you, sir.
All right. Thank you.
Today's session is over.
So today's sessions have been ended. Tomorrow we will meet at 10 a.m. in the morning.
Okay, but the same link,
Same time, same.
link. It's okay.
Okay.
Yes, same link.
So, attendance is being recorded automatically. We will send the feedback link on Sunday after all the sessions will be ended. Then we will provide you the feedback link as well as the certificate link. You will get the certificate if you have attended all the sessions. Thank you very much.
Thank you.